Hi everyone, our today's lecture is on Thevenin's equivalent circuit. So I guess you already know equivalent resistance, right? If you remember that equivalent resistance is actually replacing several resistance by just one resistance. For example, if there are two resistances are in series, say this is 5 ohm and this is 10 ohm, we can replace this combination by a single resistance of 15 ohm, and this was the process that we called equivalent resistance, right? Because this resistance is doing the exact same thing as the combination of these two resistances. So Thevenin's equivalent circuit is actually some sort of equivalence like this one, but it will be equivalence of a whole circuit. That means if you have a complex circuit, you can symbolize or you can represent that complex circuit using very simple voltage source and resistance, and there's actually the concept of Thevenin's equivalent circuit. Let me start with a very basic example. Let's consider that you have a phone charger, and if you open the phone charger, you will see that there are a number of components. And surely, as you can see that this circuit is very complex. But somehow, if you can represent the circuit with just one voltage source and a resistance, then it would be pretty much easy, right? And that's actually the concept of Thevenin's equivalent circuit. Thevenin's equivalent circuit tells us that any circuit can be represented with only one voltage source and only one resistance. Now, since we are engineers, so this example will focus on more like theoretical concept of finding the Thevenin's equivalent circuit. For that, let's consider a circuit like this. You have a 10 volt voltage source, and let's say there is a resistance of 5 ohm. Let's consider that there is another resistance which is say 10 ohm, and there are two more resistance. One is 2 ohm, and let's say there is another one which is 8 ohm. Now let's say I want to find the voltage across this resistance, and let's call it V1. That means we have a circuit where I am required to find the voltage across this 8 ohm resistance, and also I want to find the current through this resistance, which is, let's say, I1. Okay. To find this thing, what we can do, we can assume that the whole current is going through this. Let's say this is I, and if we can find the value of I, then we can easily find the value of I1. And using V equals to IR formula, we can easily find the voltage of this circuit, right? So first, we want to find the overall current of the whole circuit. To find the overall current, I need to find the overall resistance of the circuit. And if you calculate this whole circuit, the equivalent resistance will be 5 plus another 5. It will be 10 ohm. So the current I will be voltage, which is 10 volt, divided by the overall circuit resistance, which is 10 ohm, and that gives you 1 ampere. So we have found the value of I. Now we can easily find the value of I1, and that would be very easy because I will be divided into two parts. One will go through this 10 ohm resistance, that means through this branch, and another one will go through this one. And if you examine that this branch has a resistance of 10 ohm, and this branch also has a total resistance of 10 ohm, that means the current will be divided equally. That means 0.5 ampere will go through this branch, and another 0.5 ampere will go through this branch. So I am not applying any current divider rule here. Just from analyzing, I can say that I1 is actually half of I, or 1 over 2, that is half ampere. So since I now know the value of I1, I can also find the value of V1, because V equals to I times R, and the value of resistance is 8 ohm. So the value of I is 0.5 times 8 equals to 4 volt. So we have found the voltage. The value of the voltage is 4 volt, and we have also found the current, which is 0.5 amperes. So we will keep these values. That means the value of V1 is 4 volt and the value of I1 is 0.5 ampere, because I need these values for proceeding further with the example. Now let's draw another circuit where there is only one voltage source and only one resistance, and across the output of this two terminal we are connecting our previous 8 ohm resistance. And now let's consider the voltage source is 6.67 volt and the resistance is 5.33 ohm. Now let's again find the current. Say now it is I prime, and let's again find the voltage, which is say V prime. We can find the value of I prime very easily because now there is only one branch here. So in order to find the value of I prime, we can just divide the voltage divided by the overall resistance, which will be 13.33, and let's see what we get. And if you calculate the value, it will be very close to 0.5. So we can write the current is again 0.5 ampere. Since the current is 0.5 ampere, we can again find the voltage by multiplying the current with the resistance, and again you will get the 4 volt. That means since although we have changed the voltage source along with the resistance in this circuit, but we have got the values which is exactly as our previous values, right? So remember, these values we got from this circuit where there are 3 resistance along with this 8 ohm resistance, and there was a voltage source of 10 volt. But these values were obtained from this circuit where there is only one voltage source and only one resistance. But the values are exactly similar, right? From this analysis, we can say that this part of the circuit, that means the part of circuit up to this 8 ohm resistance, that means this part of the circuit is actually doing the same thing as this part of the circuit, right? That means in this circuit there were 3 resistance and 1 voltage source connected with 8 ohm resistance, and in this circuit there was only 1 voltage source and only 1 resistance connected with this 8 ohm resistance. If we consider that this 8 ohm resistance is our load, that means this combination and this combination is doing the exact same thing, right? And there's actually the Thevenin's equivalent circuit. That means if we represent any circuit with just 1 voltage source and 1 resistance, then this combination is actually the Thevenin's equivalence of that circuit. That means we have to find such a circuit which delivers the same amount of current and same amount of voltage across the output terminal, and then we can call that circuit is the Thevenin's equivalent circuit of the previous one. Now there may be a question that how did I get that 6.67 volt and this 5.33 ohm resistance, right? Because if you try different any other combination, it may not give you it will because if you try any other combination, it will not give you the exact same voltage and current that you obtained here. Because if you try any other combination, it may or may not give you the exact same thing here, right? So we have Because if you try any other combination of voltage and voltage source and resistance here, it may or may not give you the same thing, and it's not something iterative process, right? You cannot just randomize or randomly put any voltage here or randomly put any resistance here to find the equivalent circuit. So there are some methods to determine the Thevenin's equivalent circuit, because if you try any other combination, it may or may not give you the exact same voltage and exact same current. So it's not something to be guessed. That means you cannot just go through iterative process to find the Thevenin's equivalent voltage and resistance. What I actually did is that I actually solved this Thevenin's equivalent circuit of this one and put it here to provide you the example. Now I will show you how I actually computed the value of this voltage source and the resistance. Okay, because these are the two things that just two things you will need to find to determine the Thevenin's equivalent circuit of a big circuit. Okay, now let's recall our previous circuit. There was a voltage source, resistance of 5 ohm, another resistance of 10 ohm here, another 2 ohm resistance here, and since we want to determine the Thevenin's equivalent circuit of this one, remember there was a 8 ohm resistance here, right? But that we actually considered as a load. So for now, to determine the Thevenin's equivalent circuit, we will eliminate the load here. So to find the Thevenin's equivalent circuit, we will just erase the load and keep the remaining of the circuit. And let's call this node as A and this node B. So all you need to do is to find the equivalent resistance between the nodes A and B, and you need to find the voltage across the nodes A and B. That means resistance and the voltage source. That's all you need. Okay, remember this is a very simple example, but the procedure that we are going to use here can be applied to any circuits. Okay, so the first thing that you need to do, step number one, first step is to remove all the active sources, active and independent sources. For example, in this circuit, we have a voltage source of 10 volt. So we need to remove this 10 volt. That means we have to turn off. By the word turn off, I don't mean that you just erase this voltage source, or if there is a current source, you just erase that thing. Rather, by turn off, there are actually two interpretations of turn off, such as if you have a voltage source and if you turn it off, you are required to set the voltage to 0 volt, and if you have a current source, you are required to set the current as 0 ampere. What I mean, let's say there is a resistance here and there is a voltage source here. Okay, let's say this have a 50 volt supply and say this is 100 ohm resistance. Now if I want to turn this off, I have to set the voltage as 0 volt, and if I set any voltage source to 0 volt, it then means that the voltage source has been turned off for our case. Okay, so that means turning off means converting a voltage source to a 0 volt supply and converting a current source to 0 ampere supply. Now we have a very easy way to do that. Ideally, a conductor has 0 resistance, and that's why it has a 0 voltage drop. See, 0 resistance means 0 voltage drop. So to obtain a 0 volt drop, what we need to do is actually short the two terminals of the voltage source. That's it. That means we will replace this voltage source with a short circuit. That's all. So there's the way you set a voltage source to 0, or you turn off a voltage source to find the Thevenin's equivalent circuit. That means you had to replace voltage source with a short circuit. So I think you have already guessed what you need to do for a current source. Well, you need to make it an open circuit. That means if there is a current source anywhere, say this is terminal A, this is terminal B, you just have to remove that thing, which means you have to just open circuit to get a 0 ampere current, because since there is no connection in between A and B, there will be no current flowing through here, right? So the amount of current here is 0 ampere. But to turn off a voltage source, we need to short that thing, because if you short two terminals, then the voltage across this two terminal will give you 0 volts. Say this is A and this is B here. So if you short A and B, then the voltage across A and B is now 0 volt. So all you need to do is to actually replace something. And what to replace? Replace a voltage source with short circuit, and replace a current source with open circuit. So in our previous example, there was only one voltage source. So what we will do with this voltage source, we will actually short this two terminal. And remember, this step number one is done to obtain the Thevenin equivalent resistance. That means we will proceed with this step number 1 in order to find the Thevenin's equivalent resistance. And by Thevenin's equivalent resistance, what I mean is, if you remember, in Thevenin circuit, equivalent circuit, there will be only one voltage source and there will be only one resistance. This resistance is called RTH, or Thevenin's equivalent resistance of a big circuit, okay, like this one. And there is a voltage source which is called VTH, and VTH is actually the equivalent voltage source for the big circuit. Okay, so by Thevenin's equivalent resistance, we will actually mean this resistance, and Thevenin's equivalent voltage will mean actually this voltage source. Okay, so step number 1 will help us to determine the value of RTH. So under step number 1, the first thing you have to do is to replace all the active and independent voltage sources and current sources with short circuit and open circuit, and use step number 2, which is actually linked to step number 1. Remember, these two steps will give us the value of RTH. Okay, and remember, we have to keep in our mind the two terminals A and B. Like here, we numbered this as A and this B. So in order to find the Thevenin's equivalent resistance, this is the first step, and in the second step, you will actually find the equivalent resistance across A and B. So first we have to remove the load and provide A and B to the terminals that across which we want to find the Thevenin's equivalent circuit. Then in step number 1, we have to turn off all the voltage and current sources, and in step number 2, after completing the step number 1, in step number 2, we will just find the equivalent resistance across A and B. And to find the equivalent resistance, there are lots of ways, such as you can use some series parallel combinations to find the equivalent resistance that we discussed in our classes previously. And also you can use node method, okay, nodal analysis method to find the equivalent resistance. There are lots of ways. For this circuit, this is a very easy circuit, so just using series and parallel equations, that means just analyzing the series and parallel combinations of the resistances will be enough to solve this circuit that we are dealing now. Okay, so if we remove the voltage source by a short circuit and keep all other things intact, then our circuit will look like this, right? This was my A terminal and this was my B terminal. This resistance had a value of 5 ohm, this one 2 ohm, and this one is 10 ohm. Now by observation you can see that this 5 ohm and 10 ohm is actually in parallel, because the first terminal are connected here and the other terminal is connected here. That means 5 ohm and 10 ohm are in parallel. So if I find the parallel equivalence of these two resistances, then I will get 1 over 5 plus 1 over 10 inverse 1. And that will give me 3.33 ohm resistance. That means now I can replace these two resistance with just one resistance of 3.33 ohm, and there was a 2 ohm resistance intact here at terminal A, and this is my terminal B. So now these two resistances are in series, so 2 plus 3.33 will give you a 5.33 ohm resistance. That means across my terminal A and B, the equivalent resistance is 5.33 ohm. This is pretty simple task because you have done more complex things in your classes. So the resistance that you found across the terminal A and B that we defined previously is actually your Thevenin's equivalent resistance, that means RTH. Okay, so congratulations, you have found the value of Thevenin's equivalent resistance. That means in our circuit, Thevenin's circuit, there were two components. One was RTH, another one was VTH. We have already found the value of RTH. That's simple. Okay, now we will use step number 3, and this step 3 will help us to determine the Thevenin's equivalent voltage. Okay, so in step number 3 we will actually keep everything as our main circuit, and my favorite way is to apply KVL and find the VTH. Okay, that means step number 3 will help us to determine the value of VTH, and in step number 3 the first thing that you will do is revert everything to our normal circuit. That means we have to go back to our main circuit, because in this circuit we removed the voltage source, right, with a short circuit. That was our step number 1. And after removing the voltage source, then we used series parallel combination to find the equivalent resistance, which we did here. We found the equivalent resistance between A and B terminal, which is 5.33 ohm, and that's actually our RTH. So with step number 1 and 2 we have found the value of RTH. Okay, remember when there will be some dependent sources, we will actually use a different method to find the value of RTH. So now in step number 3, since we are focused on finding the value of VTH, we have to go back to our original circuit. That means we cannot remove anything. So our previous circuit was a 10 volt supply with 1.5 ohm resistance here and the 10 ohm resistance here. There is a 2 ohm resistance here and terminal A and B. And let's also call the voltage between this terminal A and B as VAB. Okay, now as you can see that there are two loops here. This is my loop number 1. Let's say this is this loop has a current of I1, and this is my loop number 2. and in this loop let's consider there is another current I2. So someone will argue that there will be no current through this resistance, right? Because as you can see that there is nothing connected between A and B. That means A and B is some open terminal, right? So since there is nothing connected to A and B, current will not flow through this terminal. So from this we can directly say that the value of I2 is actually 0 because nothing is connected here. Or you can imagine there is a resistance here which is infinity, because an open circuit has a resistance, has a theoretical resistance of infinity, right? So if there is infinite resistance in a branch, then the amount of current that will go through that branch is actually 0. So that means the loop current I2 is 0. So now you may say that then why did we actually encounter this loop, right? That's because we need to find the value of VAB. So you can find the value of VAB by other ways that I will show you later, but for now just stick to this example where I will be using KVL to determine the value of VAB. Okay. Now if I apply loop equation in loop number 1, then what we get minus 10 plus 5I1 plus 10 I1 minus I2 is equals to 0. Now remember the value of I2 is already 0, right? So if I put this value here, then I will get minus 10 plus 5 I1 plus 10 I1 equals to 0. That means 15 I1 is equals to 10. Therefore I1 is equals to 10 divided by 15 ampere. You can go forward and find the fractional value of I1, but I will just give you can find the decimal value of I1, but I will just keep this fraction here. Now if I apply the loop equation in loop number 2, then what I get, I will write it in side by side ways. So first let's start with this terminal. So we'll encounter a 10 ohm resistance here. So it will be 10 I2 minus I1, right? Because this is a shared branch between I2 and I1, and there will be another 2 ohm resistance, and it will give you 2 I2. Now what we'll do here, we will use this VAV as a whole to complete this loop equation. You know, in KVL, what we actually do, we actually find all the voltages, right? That means we find this voltage, this voltage, this voltage, and if you add all the voltages in a loop, then it will give you 0. That's actually the KVL equation, right? For example, in our equation number 1, what we actually did, we actually found the voltage of this one, we found the voltage of this one, we found the voltage of this one, and added together all of those things, and we got 0. That's actually our summation of V equals to 0, or KVL equation, right? This is the main concept of KVL. So here what I'm gonna do is that I will just directly use this voltage here. Okay, that means I'll not represent this VAB as IR, because if there is a resistance, I can represent it as voltage. Say the voltage of 5 ohm is actually I into R. Similarly, the voltage of this 10 ohm resistance is I into R. So in this way you can determine the voltage across any resistance. But here, since there is a resistance of infinity, I will not use that thing. Rather, I will directly use the voltage across these two terminal here. Okay. Now if you put the value of I2 and I1, now because I have already found the value of I1, now it will be very easy to put the value of I2 and I1 here. So it will give you 0 minus 10 by 15. Remember the value of I2 is 0, so 2 times 0 is 0, plus VAV remains 0. So 10, there will be minus 10 by 15 here, plus VAB equals to 0. And if you transfer the side, then what you will get, VAV equals to 100 divided by 15, which is 6.67 volt. Now the voltage across these two terminals, that means A and B, which we wrote as VAB, is actually our VTH, that means Thevenin's equivalent voltage. Since we have found the value of VAV, that's actually our voltage of value of VTH. Since because these two things are actually the same thing, the voltage across the terminal A and B is actually our Thevenin's equivalent voltage. So VTH is 6.67. So using step number 1 and 2, we actually determined the value of RTH, which was 5.33 ohm. And using step number 3 and applying KVL, we actually determined the value of VAB, which is actually VTH, and we obtained the value as 6.67. And that's actually the values that I used to demonstrate in our previous example: a voltage source of 6.67 and a resistance of 5.33. That's how you have to calculate the value of VTH and the value of RTH. And this is the last step, that means step number 4. In this step, what you will do, you will just draw a voltage source, you will draw a resistance, and put the obtained value of the VTH and the RTH, and naming the terminal A and B is actually our Thevenin's equivalent circuit. Because this circuit actually does the same thing as of the big circuit, right? So let's rewind everything. What was a Thevenin's equivalent circuit? It was actually representation of a big circuit with just one voltage source and one resistance that will give you the same voltage and same current. That was actually the Thevenin's equivalent voltage and Thevenin's equivalent resistance and overall Thevenin's equivalent circuit concept. Okay. In order to find the value of voltage source and the value of resistance, we actually followed 4 steps. In our step number 1, we actually replaced all the independent and active sources to 0. And in order to do that, you have to replace all the voltage sources with short circuit and all the current sources with open circuit. And after that, use any convenient method to determine the voltage across the predefined nodes A and B, and that will be your value of RTH that we did here. So when you have found the value of RTH, now it's time to find the value of VTH. To find the value of VTH, we will go back to our original circuit. My favorite way is to apply the KVL. There are other ways, I will show you. My favorite way is to apply the KVL. So after obtaining the value of VTH and RTH, what you have to do is actually draw just one voltage source and one resistance, and write the obtained voltage, Thevenin's equivalent voltage, and write the obtained Thevenin's equivalent resistance, and there's actually your Thevenin's equivalent circuit. So that's all for today, and I hope that you are staying at your home. And do not go outside without any emergency. Try to do something productive. Try to utilize the time. And see you in the next lecture.